Hello. Does this sound all right? Sounds good? Okay. Good afternoon. My name is Mark Werner. I work for TerraPower in engineering, and today I'll talk a little bit about our Natrium project, which is going on in Wyoming currently. For those of you who don't know, the Natrium technology is a Gen 4 reactor getting developed by TerraPower and a number of partners. We're located in Washington State in the United States. TerraPower is a sodium fast reactor coupled to integrated energy system. That integrated energy system is a molten salt thermal storage system integrated directly into our plant. The reactor is about 345 megawatts equivalent, but using that integrated energy system, we can peak our power up to 500 megawatts for up to 5.5 hours. This peaking capacity allows us to do dynamic load following on the grid, increasing power at 8 to 10% power per minute. This allows us to chase daily load following on the grid and be able to meet utilities' needs as our electricity demand grows. This energy storage system is gigawatt-hour scale energy storage, much larger than current commercial battery offerings, and will really be able to dynamically change the grid of tomorrow. The sodium fast reactor, coupled with a metal fuel technology and a pool-style configuration, really increases the safety and resiliency of our reactor technology when compared to traditional reactors. Our reactor is a low near atmospheric pressure system. This allows our reactor structures to be much thinner and easier to manufacture. It allows our civil design to be needing to less retain pressure releases. Both design features allow us to reduce capital cost of our technology. The sodium fast reactor in a pool-style configuration also allows us to have very robust and safe passive safety systems that are always on. They never need to be actuated. So in case of real extreme events, the passive cooling to remove decay heat is always there. So between the low pressure systems and the robust safety case, we're really allowed to provide tremendous value and low cost with our advanced reactor technology. Both of these things combined also allow us to have a very small EPZ, which helps us site reactors in challenging locations where we're near boundaries. It also allows us to lower the operating costs because the operator doesn't need to pay for keeping a large EPC going. On top of that, the high temperature of a sodium fast reactor allows us to have a more efficient thermal cycle, creating more electricity with the same amount of heat. One of the key features we've implemented in Natrium is a decoupling benefit. We are able to decouple our reactor technology from our energy island in 3 key ways. We have operational decoupling, physical decoupling, and regulatory decoupling. We've already issued and gotten approved by the NRC to decouple our plant, the nuclear island and energy island. And what that decoupling means to us is that there's nothing that initiates or starts on the energy island that affects the safety and operations of our plant on the nuclear island. So that decoupling and regulatory space allows us to construct the energy island in advance of a construction permit application. It means that all the equipment on the energy island has no safety functions and does not need any nuclear quality applied to it. So we can construct the whole energy island to commercial standards using commercial suppliers. We can start construction before in the US before the CPA is issued, and that allows us to construct the plant faster and quicker for less capital. All while the nuclear island, which is governed by the NRC, by the regulator, is a much smaller footprint. When we apply traditional LWR safety classifications to the Natrium layout, which is shown here to the upper right, you could see that much of the plant would receive more nuclear safety applied, which would increase cost over a baseline. But when you take the Natrium technology with its more robust safety case and the decoupled stance, we're actually able to lower the applicable nuclear quality requirements and lower cost over a more substantial part of the plant. And this is one of the reasons how we're able to drive down capital costs and shorten our construction times. Now, this technology that we've developed over the years is, to develop deploy any type of first-of-a-kind technology is very expensive. Luckily, the Department of Energy decided to award us an Advanced Reactor Demonstration Project Award, which is a 50-50 public-private partnership between us and the Department of Energy. So they cost share this project with us, which is a great investment in advancing nuclear energy in the U.S. Under this partnership, we will license the plant using the NRC's 10 CFR Part 50 process, which is a two-part process. First is the construction permit application, and once that's approved, that's followed by an operational license application. Under this partnership or this project, we'll advance our technology from first of a kind to a demonstrated commercial technology. Part of this project has us developing our HALEU fuel supply, designing, licensing, constructing our Cat 2 fuel fabrication facility. We'll also deploy the first initial core load of our Natrium fuel under this project. Another part of the project is that we get to advance our equipment, nuclear equipment supply chain, and we're able to develop a sodium test facility where we're able to qualify all of our large-scale sodium equipment. And lastly, TerraPower will be the operator for this first plant, and so part of this project is developing and training our Natrium operations organization. So all those elements are what roll up to our first-of-a-kind technology project, which is cost-shared by the Department of Energy. One of the key things in developing the technology and the concept is integration with the supply chain. As designers, we can design lots of great concepts, but until you make them, you don't know if they work. So concept evolution has to go hand in hand with supply chain development. And it's great being at this conference and meeting all of our suppliers and potential future suppliers this week. Design integration or design progression requires integration with manufacturers, operators, designers, and owners to get to a great solution. We are very interested in design progression that involves fabrication and manufacturing with mock-ups and prototypes. And finally, you really do need to push the design to finality before you go to full mobilization of construction, or else you'll be just changing your design as you're trying to build it. So new projects like ours require extensive supply chain development, and that really requires early strategic supply chain selection. So it's very important to us to find good strategic suppliers that we want to integrate with and get on board, and we treat them like partners, they treat us like partners, and we iterate on the design, and that is how we move the design forward. These strategic suppliers provide very valuable design for manufacturing input to us during the concept and final design phases. And then once again, design finality is very important and required for fabrication release. So where are we? Like I said earlier, we're doing a two-part application process with the NRC. We submitted our CPA in March of 2024, and that was accepted by the NRC for review. We've recently received the final environmental impact statement last month, and we anticipate the final safety analysis review done by December, and we anticipate the full CPA to be approved either by end of this year or by February of next year. So that with that approved CPA, we'll be able to start first nuclear construction Q1 of next year. Earlier this year, we completed a preliminary design of the whole entire plant in Q1 of 2025, and that was a 2-year effort to get the design from conceptual stage to preliminary stage. With that design state, we're able to start initiating long lead material releases. We're able to execute level 1, level 2 cost estimates, and effectively plan the remainder of our project. Currently, 6 months past Q1, we're in detailed and final design, and we're moving towards completing the design in next year. At this moment, 100% of our long lead equipment are under order, under contract on the nuclear island, and our entire reactor enclosure system, which is kind of the key part of this integral fast reactor, is being worked by our supply chain. Another big key part of the Natrium development or deployment program is our fuel supply, and we do have our fuel supply covered. We've got a source for our HALEU and ASAP isotopes. We've got our metallization process covered by Framatome. And lastly, our fuel fabrication vendor, GNF, has started the design and of our fuel fabrication facility, which will be in Wilmington, North Carolina. This map shows our current supply chain. These are vendors that we've selected and awarded to over the last couple years. As you can see, we've got a great mix of both domestic in the US and international suppliers. With our demonstration project being a DOE cost share, they do prefer us to go with domestic suppliers, but we're able to reach into international supply chain where it's advantageous to us. A lot of these suppliers are great strategic suppliers, and we've brought them in early to help us iterate on the design as we design it before we release for fabrication. And many of these suppliers are here this week. We have BWXT Canada and Marmin working on large equipment for us. We have a healthy South Korean supply chain in Doosan and HD Hyundai. And then domestically, we have Curtiss Wright working on a lot of INC systems for us. Framatome working on fuel handling equipment. Hayward Tyler working on pumps. Mirion working on other INC systems for us. Orno working on pull racks and others. So this represents a lot of the supply chain development work we've done over the last couple years in combination with our design development work to move our project forward. And all that comes to our construction site. We broke ground on our construction site in June of 2024. It is a mobilized construction site, and we're working on it today. Initially, we're working on several non-nuclear facilities. We're working on a test and fill facility. And in that test facility is where we'll test full-scale sodium-wetted equipment, full-scale in sodium at prototypic conditions. So that facility is, we're erecting steel right now. We'll be undercover by the end of the year, and that facility will be operational by the end of next year. We've also started constructing our training center on site, and the training center will house our reference plant simulator. And in that facility, we'll actually develop and train our first class of Natrium operators. And so that facility will be completed in 2026. The reference simulator will be qualified in 2026, and we'll start training trainers the following year. Like I said earlier, we'll mobilize the full nuclear construction site next year and start pouring nuclear concrete, which is exciting. So with that, just wanted to give an overview of the Natrium project, the technology that we have, the efforts we've gone through to advance the design, tightly coupled between the design and the supply chain, and lastly, where we are with the construction project with a view into our future. So with that, appreciate everyone coming today. There's a bunch of TerraPower and partner people here in the audience, and if anyone has any questions, swing on by. Thank you.